So now I want to prove a key fact about compactness, which is that the product of two topological spaces, the two compact topological spaces, if I give it the product topology, then the product is again compact. Before we get into proving that, I just need to introduce some slightly more flexible terminology that we're going to use in the middle of the proof. The definition is like this. So let X be a topological space. And I suppose I've got some open cover. Of X. And let's suppose that K is some subspace of X. Then we say K is finitely covered if a finite subset J of the index set I such that K is contained in the union of the corresponding U's. Okay, so to say that there's a finite subcover, that just means that the whole space X is finitely covered. In order to prove that, in particular cases, we might want to sort of build up to it by proving that certain subsets are finitely covered first. Okay, so that's terminology we're going to use in the proof. So the theorem will now state more formally. Suppose that Y and Z are topological spaces. Are compact topological spaces. Okay. So then the claim is that Y cross Z, with as usual the product topology, is also compact. Okay, so how does the proof start? Well, as any direct proof of compactness starts, we say let suppose we've got a finite an open cover. Okay, so now we need to show that there's a finite subcover. In order to produce that, as I say, we're going to build up to that by proving that certain subsets of Y cross Z are finitely covered. Okay, so let's just write that again. Y and Z are compact. And then you've got some open cover UI of the space Y cross Z. And so our initial claim is that so for each Y in Y, as an open set SY of the space capital Y, with Y as an element of this SY, and if we look at the product SY cross Z is finitely covered. So this, if you think of kind of Y is going horizontal, Z is going vertical, then so SY is like a little interval in the horizontal direction, and then so this SY cross Z is like a vertical stripe, and the claim is that this vertical stripe is finitely covered. Okay, so proof so for each z, well, the point yz, well, you know, so that's some point in y cross z, and y cross z is covered by these sets ui. So there's some index IYZ which so one of these sets ui must contain y comma z. So we can pick some index IYZ such that what the pair y comma z lies in there. Now we know that UIYZ is open in the product topology. If you recall how the product topology is defined, that means that there's a box which we can call, say, VYZ cross WYZ, and where Y is in the V set, Z is in the W set, and VYZ cross WYZ is in this U. Okay, so we've got all these sets like this. Now, so in particular, yeah, so Z is in WYZ. So if we look at the family of these, we're keeping this Y fixed and allowing Z to vary. If we look at these WYZ with for all Z in Z, okay, so these because Z lies in WYZ, that means that we take all the WYZ, so that's an open cover of the space Z, but Z was compact. So that means we can choose some finite list, Z1 up to ZR, say, such that Z is the union of those corresponding W things. Okay, so so now we can put SY. SY we can define to be the intersection of the corresponding V sets. Okay, so yeah, so this is what our SY is. And we were supposed to be proving there's an open set SY which contains Y and has the property that SY cross Z is finitely covered. So we need to check those properties. So two of them are kind of straightforward. Okay, so we've got well, firstly, this is the intersection of these V's. So this is an intersection of finite list of open sets, so intersection of any finite list of open sets is open. So that's open. And Y lies in each of the sets V, Y, comma Z. Remember, that's what we wrote here. Y is always in V, Y, Z. So Y is in each of these sets here, and so therefore it lies in the intersection. So so this set SY is open and contains Y, but we still need to check this claim that this set SY cross Z is finitely covered. Okay, so we need to show that SY cross Z is finitely covered. So should be contained in some finite union of these things. So which ones are we going to use? So we're going to have U I Y comma Z1 up to U I Y comma ZR. Right, so remember where did these ZI's come from? That was we showed that the sets W, Y, Z covered the whole of Z, and so we had some finite list of Z's which such that the corresponding W's were a cover. Okay, so why is this true? Suppose we've got some A comma B lying in this set SY cross Z. And so remember the point about this list of ZI's was that Z is contained in WY comma Z1 to WY comma ZR. So that means we can choose T with the second point B, right? Remember here we had some A comma B here. A was in SY, B was in Z, and Z is contained in this union, so it must be contained in one of these sets. So B we can assume is in WY comma ZT. Okay. Now so Y was in SY, okay, and then SY is WY, V, this is VY comma Z1 intersect up to VY comma ZR. Okay, so this is an intersection of a bunch of sets, and one of those sets is VY comma ZT, okay, where this T was like this. Okay, so this intersection is contained in each of its terms, so it's contained in here. So now we, this was our point A, right? A here is in SY, and SY is this intersection, so A is in this thing here. So this means that the pair A comma B, that's in VY comma ZT cross with W Y comma ZT. Okay. But the whole point about these V's and W's was that this was a box that's contained in the open set U I Y comma ZT. And so this works for any so this is contained in this union here. Okay, and that's what we were supposed to be proving. Okay, so so now we see that SY cross Z is finitely covered. Okay, so we're on the right track, but we're not quite finished yet, because we're supposed to be proving that there's a finite subcover. In other words, we're supposed to be proving that the whole space Y cross Z is finitely covered. So we need an extra step for that. Okay, so let's just remind ourselves what we proved. So for each Y and Y, there's an open set SY containing Y, such that the stripe SY cross Z is finitely covered. Okay. Now let's look at all these open sets SY. Okay, so each one of them is open, as we've said, and it contains Y, so that means that if we take all of them together, So these give us an open subspace, an open cover of Y, which is a compact space. So that means we can choose a finite subcover. In other words, some finite list of indices such that Y is contained in SY1, or Y is actually equal to SY1 union up to SYM. So each set SYK cross Z is finitely covered. Okay, and it's clear that if you take the union of finitely many sets, each of which is finitely covered, then it's still going to be finitely covered. So we find SY1 cross Z up to SYM cross Z is finitely covered. But this, of course, is just equal to SY1 union up to SYM cross Z, which is Y cross Z. So that means we have a finite subcover for all of Y cross Z. Okay, so we've proved that if you start with any open cover of Y cross Z, then by this kind of two-step process, we get a finite subcover of the whole space, and that's precisely what it means to say that Y cross Z is compact, which was the theorem we were supposed to be proving.